Picture this: a supermassive black hole, millions of times the Sun's mass, lurking in the heart of a distant galaxy. Now imagine its event horizon, a point of no return, being fed by a swirling disk of gas and dust, glowing like a cosmic kitchen stove. This is what James Webb Space Telescope has finally captured in vivid detail, revealing how these monsters sustain themselves. For the first time, astronomers have observed the precise dance of material spiraling inward, heating up to millions of degrees and emitting light so intense it outshines entire galaxies. The telescope's infrared eyes pierce through cosmic dust to witness this process, uncovering a mechanism that's been hidden for eons. It's not just about swallowing stars, it's about orchestrating a celestial feast, where gravity and radiation collide. And in this dazzling spectacle, the secrets of how black holes grow and how they shape the universe finally come into focus. For decades, scientists have puzzled over how supermassive black holes, which reside at the centers of galaxies, manage to sustain themselves. These cosmic entities, millions or even billions of times more massive than our Sun, consume vast amounts of gas and dust, yet their feeding mechanisms remained elusive. Now, the James Webb Space Telescope has provided the first clear glimpse into this process, revealing how these black holes not only feed but also shape the galaxies they inhabit. The discovery is a milestone in astrophysics, offering new insights into the life cycles of black holes and their role in the universe's evolution. At the heart of this revelation is the observation of how supermassive black holes accrete matter, pull in gas, dust, and other materials from their surroundings. Previous telescopes, like the Hubble Space Telescope, could only observe the glowing halos of light surrounding these black holes, known as accretion disks. But the James Webb Space Telescope, with its advanced infrared capabilities, has allowed astronomers to peer deeper into these regions, capturing details that were previously invisible. What they found is a dynamic and complex process that explains how black holes sustain themselves over billions of years. The key to understanding this process lies in the behavior of gas and dust near a black hole. When these materials approach the event horizon, the point of no return, their intense gravitational pull accelerates them into a swirling disk of superheated plasma. As the gas spirals inward, it heats up to millions of degrees, emitting vast amounts of energy in the form of light, primarily in the infrared spectrum. This is why black holes, despite their darkness, are often surrounded by luminous accretion disks. However, the James Webb Space Telescope has gone beyond just observing this glow. It has revealed the intricate interplay between the black hole's gravity and the surrounding material, showing how the black hole doesn't just passively consume its surroundings but actively regulates its own feeding. One of the most surprising findings is the role of magnetic fields in this process. The telescope's observations suggest that the magnetic forces around the black hole act like a cosmic conveyor belt, channeling gas and dust into the accretion disk. These magnetic fields also play a critical role in determining the rate at which the black hole consumes material. When the magnetic pressure becomes too strong, it can slow down the inflow of gas, creating a balance that allows the black hole to sustain itself over long periods. This balance is essential because if a black hole consumed its surroundings too quickly, it would exhaust its fuel and become inactive. Conversely, if it consumed too slowly, it might not grow to its massive size. The James Webb Space Telescope has shown that this delicate equilibrium is maintained through a combination of gravity, magnetic fields, and the intense radiation emitted by the accretion disk. Another critical aspect of the discovery is the connection between black hole feeding and the surrounding galaxy. As the black hole pulls in gas and dust, it releases enormous amounts of energy in the form of radiation and high-energy particles. This energy can influence the surrounding environment, heating up the interstellar medium and potentially stifling the formation of new stars. This phenomenon, known as feedback, is thought to regulate galaxy growth. However, the James Webb Space Telescope has provided the first direct evidence of how this feedback mechanism operates. By analyzing the light emitted from the accretion disk, astronomers have determined that the energy released by the black hole can either suppress or stimulate star formation in its host galaxy, depending on the specific conditions. This finding underscores the profound impact that black holes have on their cosmic neighborhoods, acting as both engines of destruction and catalysts for creation. The implications of this discovery extend far beyond the immediate understanding of black hole behavior. For years, scientists have debated how supermassive black holes could have grown to their immense sizes in the early universe. The James Webb Space Telescope's observations suggest that the feeding mechanisms observed in nearby galaxies may have operated in a similar way billions of years ago. This means that the process of black hole growth is not only efficient but also consistent across cosmic time, providing a framework for understanding how these objects evolved. Additionally, the telescope's ability to detect the faint infrared light emitted by accretion disks has opened new avenues for studying black holes in distant galaxies, where previous telescopes struggled to gather sufficient data. One of the most remarkable aspects of the James Webb Space Telescope's findings is the level of detail it has revealed about the accretion process. Unlike earlier observations, which often captured only the overall glow of the accretion disk, the telescope's advanced instruments have allowed astronomers to study the structure and dynamics of the gas and dust in real time. This has led to the discovery of previously unknown features, such as the presence of high-speed jets of material being ejected from the black hole's poles. These jets, composed of particles accelerated to near-light speeds, are thought to be a byproduct of the intense magnetic fields and radiation pressure within the accretion disk. While these jets themselves do not directly contribute to the black hole's feeding, they play a crucial role in distributing energy across the galaxy, further influencing star formation and the distribution of matter. The discovery also raises new questions about the relationship between black holes and their host galaxies. For example, how do the feedback mechanisms described by the James Webb Space Telescope observations affect the long-term evolution of galaxies? Do these processes vary depending on the mass of the black hole or the density of the surrounding gas? Answering these questions requires further observations and simulations, but the data gathered by the telescope has already provided a foundation for future research. Scientists are now using this information to refine models of galaxy formation and to explore the role of black holes in shaping the large-scale structure of the universe. In summary, the James Webb Space Telescope has transformed our understanding of how supermassive black holes sustain themselves. By revealing the intricate interplay between gravity, magnetic fields, and radiation, the telescope has provided a detailed picture of the accretion process that powers these cosmic giants. This discovery not only explains how black holes grow and evolve but also highlights their profound influence on the galaxies they inhabit. As scientists continue to analyze the data from the telescope, they are uncovering new layers of complexity in the universe's most mysterious objects. The journey to understand black holes is far from over, but with tools like the James Webb Space Telescope, we are now equipped to explore the cosmos with unprecedented clarity and insight. Using the James Webb Space Telescope, JWST, astronomers have gotten a glimpse at the mechanisms that supermassive black holes use to feed themselves. This part of our deep dive into James Webb Space Telescope discovers how black holes feed themselves, focuses on, walk through how scientists found or confirmed this instruments, telescopes, missions, method, timeline. Make the process itself feel impressive. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Using the James Webb Space Telescope, JWST, astronomers have gotten a glimpse at the mechanisms that supermassive black holes use to feed themselves. This part of our deep dive into James Webb Space Telescope discovers how black holes feed themselves, focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, black holes were more myth than science. The idea of a region in space where gravity is so strong not even light can escape first took shape in the early 20th century, when Albert Einstein's theory of general relativity predicted their existence. But it wasn't until the 1960s and 1970s that astronomers began to seriously consider black holes as real, physical objects. At that time, the universe was still a mystery in many ways. Scientists had only begun to map the vast distances between stars, and the tools to observe distant galaxies were still in their infancy. Yet, even with these limitations, a few groundbreaking discoveries started to hint at the presence of something extraordinary in the cosmos. One of the most pivotal moments came in the 1960s, when radio astronomers detected strange, extremely bright sources in the sky, objects that emitted vast amounts of energy but showed no visible light. These were later identified as quasars, and they became the first strong clues that supermassive black holes might exist at the centers of galaxies. Quasars are powered by accretion disks of gas and dust swirling around a central black hole, and their luminosity suggested that these black holes were devouring material at an immense rate. But how exactly did this process work? And how did scientists begin to piece together the mechanisms that allow black holes to feed themselves? The answer lies in the evolution of observational technology and the relentless pursuit of understanding the universe's most extreme environments. In the decades that followed, astronomers developed new methods to study these enigmatic objects. The 1970s and 1980s saw the rise of X-ray astronomy, which allowed scientists to detect the high-energy emissions produced when matter falls into a black hole. Instruments like the Einstein Observatory and the Rosette satellite revealed that black holes are not silent monsters but active, luminous entities. These observations confirmed that the process of accretion, where gas and dust spiral into a black hole, releases enormous amounts of energy, often outshining the entire host galaxy. However, studying this process in detail remained a challenge. The gas and dust around a black hole are often obscured by interstellar material, making it difficult to observe the inner workings of these systems. It wasn't until the 1990s that the Hubble Space Telescope changed the game. With its ability to capture high-resolution images of distant galaxies, Hubble provided astronomers with unprecedented views of active galactic nuclei, the bright centers of galaxies where supermassive black holes reside. These images revealed intricate structures around black holes, including the glowing accretion disks and the powerful jets of plasma that sometimes shoot out from their poles. Hubble's observations helped scientists refine their models of how black holes grow and evolve, but there were still gaps in the puzzle. For example, while astronomers knew that black holes could consume vast amounts of material, they struggled to understand how they sustained this process over billions of years. The key to unlocking this mystery lay in the ability to peer deeper into the universe, beyond the visible light that had long been the primary tool for astronomical observation. Enter the James Webb Space Telescope. Launched in 2021, JWST represents the culmination of decades of technological advancement and scientific curiosity. Unlike its predecessors, JWST operates primarily in the infrared spectrum, allowing it to see through the dust clouds that obscure the centers of galaxies. This capability has opened a new window into the universe, revealing details about black holes and their surroundings that were previously hidden. But JWST's role in understanding how black holes feed themselves isn't just about its advanced technology, it's also about the long history of scientific inquiry that led to this moment. The journey to uncover the mechanisms of black hole feeding began with the realization that these objects are not isolated entities but deeply connected to the evolution of galaxies themselves. In the 1980s, astronomers proposed the concept of feedback, where the energy and radiation emitted by a growing black hole influence the surrounding gas, preventing it from collapsing into new stars. This idea suggested that black holes and galaxies are locked in a kind of cosmic dance, each affecting the other's growth. However, proving this theory required observations that could capture the dynamics of this interaction over vast timescales. The 2000s saw the development of more sensitive X-ray and radio telescopes, such as the Chandra X-ray Observatory and the Atacama Large Millimeter Array, ALMA, which provided critical data on the behavior of gas around black holes. These instruments helped scientists map the flow of material into black holes and study the effects of their immense gravitational pull. Yet, even with these advancements, there were still mysteries to solve. For instance, how do black holes sustain their accretion disks over billions of years? What role do magnetic fields play in the process? And how do these mechanisms differ between different types of black holes, from stellar mass objects to the supermassive ones at the centers of galaxies? The answers to these questions required a new level of observational precision, which JWST now provides. By observing the infrared light emitted by the dust and gas surrounding black holes, JWST can trace the flow of material into these cosmic monsters in ways that were previously impossible. This has allowed scientists to study the accretion process in greater detail, revealing how black holes regulate their feeding habits and how they interact with their host galaxies. But this breakthrough wouldn't have been possible without the foundational discoveries made by earlier missions. The Hubble Space Telescope, for example, laid the groundwork by providing the first clear images of active galactic nuclei, while X-ray observatories like Chandra and XMM Newton helped map the high-energy emissions from accretion disks. These instruments worked together to build a picture of how black holes consume matter, but they couldn't see the full story. The infrared capabilities of JWST fill in the missing pieces, allowing scientists to observe the entire life cycle of material as it spirals into a black hole. This has led to a deeper understanding of the processes that govern black hole growth, from the initial stages of accretion to the eventual formation of jets and radiation that can influence entire galaxies. The historical context of these discoveries is as much about the tools and technologies that enabled them as it is about the scientific theories that guided their interpretation. Each new telescope, from the earliest radio dishes to the modern infrared observatories, has expanded the boundaries of what we can observe and understand about the universe. The journey to uncover how black holes feed themselves is a testament to the power of human curiosity and the collaborative effort of scientists across generations. It's a story that began with theoretical predictions and evolved through decades of observation, culminating in the remarkable capabilities of the James Webb Space Telescope. As we look ahead, the discoveries made possible by JWST will continue to shape our understanding of black holes and their role in the cosmos, building on the legacy of earlier missions while opening new frontiers in space exploration. While the James Webb Space Telescope has unveiled new details about how black holes feed, many questions remain. The telescope's advanced infrared capabilities have allowed astronomers to peer deeper into the cosmos than ever before, capturing images of supermassive black holes in their host galaxies. These observations have revealed intricate details about the accretion disks, swirling disks of gas and dust that orbit the event horizon of a black hole. Yet, despite these breakthroughs, the exact mechanisms by which these cosmic giants sustain themselves are still shrouded in mystery. Scientists are now grappling with a series of open questions that challenge our understanding of black hole physics and their role in the universe. One of the most perplexing mysteries is the precise process by which black holes regulate their own growth. While we know that supermassive black holes consume vast amounts of material through accretion, the details of this process remain elusive. The accretion disk itself is a dynamic environment, with gas spiraling inward at incredible speeds, heating up to temperatures that emit intense radiation. However, the exact efficiency of this process, how much energy is released and how much material actually crosses the event horizon, has not been fully quantified. Some theories suggest that magnetic fields play a critical role in funneling material toward the black hole, while others propose that turbulence within the disk is the key. The James Webb Space Telescope has provided new insights into these dynamics, but the full picture is still emerging. For instance, the telescope's ability to detect faint infrared signatures has allowed astronomers to observe how material behaves in the extreme conditions near a black hole. Yet, even with these observations, the precise interplay between magnetic forces, radiation pressure, and gravitational pull remains a topic of active research. Another unresolved question revolves around the role of feedback mechanisms in black hole evolution. Supermassive black holes are not isolated entities, they are deeply intertwined with their host galaxies. As they grow, they emit powerful jets of particles and radiation that can influence the surrounding interstellar medium. This process, known as feedback, is thought to regulate star formation in galaxies by either heating or expelling gas. However, the exact nature of this feedback and its long-term effects are still debated. Some studies suggest that the energy released by a growing black hole can suppress star formation, preventing galaxies from becoming overly massive. Others argue that the process is more complex, with periods of intense activity followed by dormancy. The James Webb Space Telescope has helped shed light on these interactions by capturing detailed images of galaxies hosting active black holes. Yet, the precise balance between the black hole's growth and its impact on the galaxy remains unclear. For example, while the telescope has revealed how radiation from a black hole can heat surrounding gas, the exact timescales and efficiency of this process are still under investigation. This feedback loop is crucial for understanding how galaxies evolve over cosmic time, but its mechanisms are far from fully understood. A third area of uncertainty is the role of dark matter in feeding black holes. While dark matter itself does not interact with electromagnetic forces, its gravitational influence is thought to shape the distribution of gas and stars in galaxies. This, in turn, could affect how material accumulates around a black hole. However, the connection between dark matter and black hole feeding is speculative. Some researchers propose that dark matter halos provide the gravitational scaffolding necessary for gas to collapse and form accretion disks. Others argue that the presence of dark matter may influence the dynamics of the accretion process in ways that are not yet fully modeled. The James Webb Space Telescope has not directly observed dark matter, but its ability to map the distribution of gas and stars in distant galaxies has provided indirect clues. These observations suggest that dark matter's role in black hole feeding is a topic worth further exploration. However, without direct evidence, the extent of this influence remains a matter of debate. Another mystery lies in the variability of black hole feeding across different scales. Supermassive black holes are found at the centers of most galaxies, but their feeding behavior may differ significantly from smaller stellar mass black holes. While stellar mass black holes are known to accrete material in bursts, the mechanisms driving their growth are distinct from those of their supermassive counterparts. The James Webb Space Telescope has allowed astronomers to study these differences in greater detail. For example, the telescope's high-resolution imaging has revealed how the accretion disks of supermassive black holes differ in structure and brightness compared to those of smaller black holes. Yet, the exact reasons for these differences are still unclear. Some theories suggest that the presence of a massive host galaxy influences the accretion process, while others propose that the sheer scale of a supermassive black hole creates unique conditions that affect how material is funneled toward it. These questions are particularly intriguing because they touch on the fundamental differences between black holes of varying sizes and their role in the universe's structure. Perhaps one of the most profound mysteries is the question of how black holes sustain themselves over cosmic timescales. Supermassive black holes are believed to have grown from much smaller seeds in the early universe, but the process by which they accumulated mass remains a puzzle. While we know that they consume gas, stars, and even entire galaxies during mergers, the precise timeline and mechanisms of this growth are still under investigation. The James Webb Space Telescope has provided new data on the early stages of black hole growth, revealing how young galaxies hosted by nascent black holes might have evolved. However, the exact sequence of events that led to the formation of the supermassive black holes we observe today is not yet clear. Some researchers propose that rapid accretion during the universe's infancy allowed black holes to grow to their massive sizes, while others suggest that mergers between smaller black holes played a more significant role. These debates highlight the complexity of black hole evolution and the need for further observations to piece together the full story. Finally, the role of magnetic fields in black hole feeding remains a topic of intense scientific inquiry. Magnetic fields are thought to play a critical role in the accretion process, as they can influence the flow of gas and the emission of radiation. However, the exact configuration and strength of these fields in the vicinity of a black hole are still poorly understood. The James Webb Space Telescope has helped detect the signatures of magnetic fields in some accretion disks, but the details of their behavior are not yet fully mapped. Some models suggest that magnetic fields can create powerful jets of plasma that extend far beyond the black hole's event horizon, while others propose that they help regulate the rate at which material is consumed. These findings are significant, but they also raise new questions about how magnetic fields interact with the extreme conditions near a black hole. For instance, how do these fields behave in the presence of intense gravitational forces? What role do they play in the formation of jets and radiation emissions? These are questions that continue to drive research in the field. In conclusion, while the James Webb Space Telescope has made groundbreaking discoveries about how black holes feed, the journey to fully understand these cosmic giants is far from over. Each observation brings new insights, but it also raises more questions. The interplay between gravity, radiation, magnetic fields, and the surrounding environment is a complex web of interactions that scientists are still unraveling. As researchers continue to analyze the data collected by the telescope, they are uncovering new layers of complexity in the life of a black hole. These open questions are not just scientific puzzles, they are essential for understanding the role of black holes in shaping the universe. The mysteries of black hole feeding are not just about the black holes themselves, they are about the very fabric of the cosmos and the forces that govern it. And as long as there are unanswered questions, the quest to unlock the secrets of the universe will continue, driven by curiosity and the relentless pursuit of knowledge. Using the James Webb Space Telescope, JWST, astronomers have gotten a glimpse at the mechanisms that supermassive black holes use to feed themselves. This part of our deep dive into James Webb Space Telescope discovers how black holes feed themselves, focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For the first time, the James Webb Space Telescope has given us a window into the mysterious process by which supermassive black holes sustain themselves. These cosmic giants, billions of times more massive than our Sun, have long been a source of fascination and fear. But how do they keep growing? Until now, scientists have only glimpsed their feeding habits indirectly, through the light they emit as matter spirals toward them. JWST has changed that. By peering deep into the universe, it has captured the intricate dance of gas and dust being pulled into these monstrous entities, revealing the mechanisms that allow them to devour stars, gas clouds, and even entire galaxies. This isn't just about black holes, it's about the very fabric of the universe, and how these cosmic engines shape the galaxies they inhabit. Let me take you through the key revelations. First, the telescope has shown that supermassive black holes don't just consume matter randomly. Instead, they feed in a structured, almost choreographed way. As gas and dust approach the event horizon, they form a swirling disk of superheated material, glowing with the energy of friction and gravity. This accretion disk is a cosmic furnace, radiating light across the electromagnetic spectrum. But here's the twist: the light we see isn't just a byproduct of the black hole's hunger. It's a signal, a clue to the physics at play. JWST's infrared vision has allowed astronomers to measure the temperature, density, and motion of this material with unprecedented precision. What they found is astonishing. The disk isn't a smooth, steady flow, it's a turbulent, clumpy mess, with streams of gas colliding and merging. These clumps, sometimes thousands of times the mass of our Sun, are the building blocks of the black hole's meal. But how does this feeding process affect the galaxy itself? The second takeaway is the profound connection between black holes and their host galaxies. As these monsters grow, they unleash torrents of energy in the form of powerful jets and radiation. This energy doesn't just heat the surrounding space, it can stoke star formation or, in some cases, suppress it entirely. JWST has uncovered evidence that the same processes fueling a black hole's growth also regulate the evolution of its galaxy. It's a cosmic feedback loop. The black hole's appetite shapes the galaxy's fate, and the galaxy's environment, in turn, influences how much the black hole can eat. This interplay is crucial for understanding how galaxies like our own formed and evolved. The third revelation is the role of dark matter in this cosmic ballet. While dark matter itself doesn't interact with light, its gravitational pull guides the flow of gas toward black holes. JWST's observations suggest that dark matter acts as a cosmic scaffolding, channeling material into the central regions of galaxies where black holes reside. Without this invisible scaffolding, the feeding process would be chaotic, and the growth of supermassive black holes might never reach the scales we observe today. These findings don't just answer questions, they raise new ones. How do these processes vary across different galaxies? What happens when a black hole's appetite outstrips its environment? And how does this scale to the earliest galaxies in the universe's history? The James Webb Space Telescope has given us tools to explore these mysteries, but the answers lie in the data we're only beginning to decipher. If you've enjoyed this deep dive, hit that subscribe button for more explorations of the cosmos. And if you have your own theories or questions about black holes, drop them in the comments, because science is always a conversation. Until next time, keep looking up.